So here we have some example on UDL shorter than the span, shorter than the span. So take down the problem. The span is 120 meter. The loading span is 8 meter and 12 kilonewton per meter is the loading magnitude. Section, mention the problem section details, is 80 meter from B support. The problem is mentioned with 80 meters from the B support. This is 80 means this is 40. We used to follow the notation. From the left it is x, from the right it is L minus x. So we can shift the statement as the x distance is from A, that is 40 meter, and L minus x from B, which is 80 meter. The possible questions are maximum negative and positive shear force and maximum bending moment at 80 meter from B. So and also absolute maximum bending moment. So these are the possible questions can be asked in this problem. So first one, maximum negative shear force. You all know that maximum negative means it is RB value. If you want to get the maximum negative in RB, place the head of the load at the section so that here there will be a unloaded portion to get a maximum of RB value. If it is head, then the backside is tail. So using this concept, you draw the ILD of shear force variation here. ILD ordinate is x by L. X is equal to 40 by 120 equal to 1 by 3 equal to 0.33. We should concentrate only on the negative diagram because we are interested in maximum negative shear force only. So place the load here so that head and tail. So it is 8 meter span. Okay. So we need this ordinate O1 to proceed with that. So we consider the negative diagram separately, and here it is 0.33. 1 by 3 is 0.33. The span is 40. This span is minus 8. 40 minus 8 is 32. How to calculate this ordinate O1? O1 equal to 0.33 is the ordinate for 40 meter distance. 0.33 is the ordinate for 40 meter distance. What is the ordinate for 32 distance? What is the ordinate for 32? So 0.33 into 32 by 40, which is 0.264. So this O1 value is 0.264. Now we have to select the area under ILD in negative shear force only. We should not consider this positive diagram at all. We need only the negative shear force this time. So the formula is area under ILD into W. So half, this is like the trapezoidal variation of the side A, here it is B. So H is equal to 8, A plus B 0.264, here it is 0.33 other end. So this is area under ILD into the load is 12. So calculate 0.264 plus 0.33 into 4 into 12, which is 28.512 kilonewton. That's this is the maximum negative shear force. Next one, maximum positive shear force. We know the criteria to find out RA as the positive value and locate the tail at the section while moving from left to right. If you want to RA to be maximum, place the tail at the section. And we already have the shear force variation at the same section 40 and 80, which is 0.33 and 0.67. In the previous case, we deal with this negative diagram. Now it is the case for the positive shear force diagram. You extend somewhat here. You superimpose the load, which is tail and head. You extend the line here. We need this ordinate O2. How we can calculate? You separately consider the triangle. This is 0.67 for the ordinate of 80. What is the ordinate of the loading distance is 8 meters span. Okay, so 80 minus 8, which is 72. So if it is O2, O2 equal to 0.67 by 80 into 72. 0.67 into 72 by 80, which is equal to 0.603. 0.603. So you have to consider the area under ILD. So the span here is 8 meter. So half, which is 8 into 0.67 plus 0.63 into the load intensity 12. Okay, 0.67 into 4 into 12, which is 61.104 kilometer. That's all. Next one, maximum bending moment. So this is also at 80 meter from B. Maximum bending moment at 80 meter from B. Now the concept is the section divided into x and L minus x, and the load is also to be divided in the same ratio. So we need to accommodate some unknown distance A, here 8 minus A, because the total length is 8 meter. So follow this x 40 and L minus x is 80. The ratio 40 by 80, which is equivalent to A by 8 minus A. So cross multiply this, 48 minus A equal to 80A, 320 minus 40A equal to 80A, 320 equal to 120A, A equal to 2.67 meter. Okay. If A equal to 2.67 meter, then 8 minus A equal to 5.33 meter. So consider the bending moment diagram. The ordinate for the bending moment variation of ILD x into L minus x by L. X is equal to 40, L minus x is equal to 80, and length is 120. 40 into 80 by 120, which is 26.67. So this ordinate is 26.67. So we need to superimpose the load with the calculated distance 2.67, here 5.33. You extend these lines into underlying ILD diagram. We need this ordinate 1 and ordinate 2 for the further calculation. So we need to calculate this distance. This is 40. 40 minus 2.67. 40 minus 2.67 is this distance 37.33. Here it is 80. So this distance is 5.33. So 80 minus 5.33 is 74.67. So you can easily calculate O1 equal to, you compare this triangle. So 26.67 by 80 into 74.67. It means that 26.67 is the ordinate for 80 meter span. What is the ordinate for 74.67? Similarly, here 26.67 by 40 into 37.33. Okay, 26.67 into 37.33 by 40. We will get both the ordinate as 24.89. Both the ordinates are 24.89. So we need to find this area. Okay. So I'm going to write here half into the span here is 2.67, here 5.33. 2.67 into 26.67 plus this ordinate O2 24.89. This is one part, left side part. plus half into 5.33 into 26.67 plus 24.89 right side part. So this is area under ILD into 12. So you will get 68.8 plus 137.4 into 12, which is equal to 2474.4 kilonewton meter. So this is the maximum bending moment at the given section. Next one, absolute maximum bending moment. So this is the maximum of maximum possibilities of locating the load. I'm going to place the center of gravity of the loading as well as center of gravity of the beam at the same location. So it is 60 meter, 60 meter and 4 meter, 4 meter. So draw the ILD variation. We have the formula x into L minus x by L. If you put x equal to L by 2 because of the midpoint, I will have L by 4 as my answer. So L by 4, 120 by 4 equal to 30. Okay. And mark at center point, it is 30. You superimpose the load in a symmetrical way because of absolute value. Okay, the span is 4 meter, 4 meter. We need this ordinate O, the same value here also. O. How we can calculate? The total span here is 80. If you deduct 4, you will get 76. So usually you can calculate 30 is the ordinate for 80. What is the value for 76? So 30 into 76 by 80. So which is 28.5 on both sides. Because of the symmetricity, both sides equal 28.5. Now we have to consider this area. So absolute maximum bending moment equal to half into 4 into 28.5 in, sorry, plus 30 plus 30. The same expression repeated on the right side also. So I put into 2 into the loading 12. So this is area under the ILD diagram. I put the calculation for one side and multiplied by 2 because of the same values, and you observe the final value 28.5 plus 30 into 2 into again 2 into 12. You will get into 2 into 2 into 12. You get 2808 kilonewton meter. 2808 kilonewton meter. If you observe this value 2800, it will be greater than all possible values of the bending moment. If you are given with some other section, you will get some value of bending moment, but all the values are lesser than the absolute maximum bending moment value. So we finished the problem. This problem is the analysis of UDL shorter than the span using ILD method. I posted one video, the same problem using conventional method. Our syllabus is mentioned only with ILD method, but even we can compare both the calculations, how much quantity of calculation involved in the conventional method, how much easier in ILD method. Okay, thank you.